So we've been investigating these polynomial congruences, and we're going to finish the story today, kind of. So we've been investigating this general problem of solving fx congruent to 0 modulo n, where f is a polynomial with integer coefficients. We have a nice way of thinking about integers, which is their canonical form, their factorization into prime powers, distinct prime powers. And that leads us to consider this set of congruences, modulo each of the prime powers. Okay, so you're splitting up the original polynomial congruence into a set of congruences, each of them, this ends at PR to the alpha r, each of them modulo a prime power. And then you solve all these individually. Each of these are problems from I equals 1 up to r. Each of these R problems has its own set of solutions. So you get a set of solutions, x, let's call it 1, 1. No, I won't try and notate it. You just get a set of solutions for each of these. And then these sets of solutions come back and we obtain solutions to the original problem via the Chinese remainder theorem. Okay, taking one solution to the first one solution to the second one, etc. Taking one solution to each of these, that gives us a bunch of congruence classes modulo these moduli here. Of course, these moduli are pairwise co-prime, so the prime numbers are distinct. So the Chinese remainder theorem allows us to lift a set of congruences modulo each of these powers of primes back to a unique congruence class modulo n, which will be a solution of this problem back here. Okay. So we've done some work with the Chinese remainder theorem. So now we have to describe, well, how do you go about solving these things? Okay, how do you go about solving each of these? So that's what we're going to look at today. We've got a result which describes it. It kind of gives an algorithm for solving these. But I'm not going to go through the proof of it at the moment. And I may not go through the proof at all. So it's kind of the one part of the course. And if I've had time at the end, we'll turn and examine the proof at it. But really, I just want to look at it now as a kind of a calculation method for obtaining the solutions of these things. Okay. So the way it's going to work is, and I think I described this before on a previous day. To solve one of these problems, to modulo a p to the alpha, we begin with the simpler problem of just the polynomial congruence modulo p. If that can't be solved, then there won't be any solutions to this. Yeah. If this original one is going to have solutions, what this result describes is a way to lift the solutions of this to solutions of f of x congruent to 0 modulo p squared. Okay, you get the idea. Applying this result again lifts them to solutions modulo p cubed. You keep lifting, keep lifting, keep lifting, and eventually you arrive at solutions to your original problem. Okay, so this result is about how you lift solutions to one of these congruences from one level, how they lift up and how they correspond to solutions at the next higher level. Okay. So what have I said there? This is page 50 now. This will involve a procedure for lifting any given solution of the congruence f of x equals 0 modulo p to the k minus 1 to one or maybe more solutions of the congruence modulo p to the k. So as well as this one solution here lifting to a solution at the next level, they can also branch. And you can also have one solution here lifting to multiple solutions modulo the next level. So the number of solutions can grow quite a lot. Okay? Each solution at one particular level can split and generate several distinct solutions at the next level. Okay? Or they may just lift uniquely. So we'll apply this repeatedly, starting off by solving these things and lifting them up to the solutions modulo whatever prime power we're looking at. Now, interestingly, in this result, the derivative of the polynomial makes an appearance. That's kind of surprising to see. Normally, we think of the derivative as being a thing to do with continuous things, functions on the real line. What's it doing in this discrete setting in number theory? So if I do get to go through the proof later on, that will be a key point to explain why the derivative is floating around here. Okay, so we'll look at the statement of it. And just to reassure you, this isn't something that you have to memorize. It's on the formula handout that you have in the exam. Struggle even to fit it on the page all at once without making it too small. That's too small. You've got it in your notes in front of you. So it's not something you have to memorize, but it is something we want to become practiced and working with. Okay, so let's dive into it. So the theorem says, consider this polynomial congruence. So this is modulo p to the a minus 1. And it's going to say the conclusions it reaches are about solutions to the same congruence, or the same polynomial, but modulo p to the a. So it's lifting from p to the a minus 1 up to p to the a. So just from some intermediate stage here, maybe the start, maybe the second last one, but from some stage here up to the next stage. Okay, so suppose this has a solution R. So suppose we've got one solution to this problem. So R is an integer, but it's representing a congruence class modulo p to the a minus 1. Okay, because those are what the solutions of the problem f of x congruent to 0 modulo p to the a minus 1 are. Their congruence class is modulo p to the a minus 1. So the first thing, so this is a bullet point list, and there's 2 items. So there's a test to do. So this is like an algorithm. Okay, so first of all, we check the value of the derivative f prime evaluated at R. And we check it modulo p, modulo whatever the prime is. And it's whether it's non-zero or 0 affects which case we go into. Okay. If it's non-zero, which is the usual case, okay, because most congruence classes are not 0, only the 0 one is 0. So most of the time, you get something non-zero, and in that case, so this is the usual case, the solution R lifts uniquely to a solution S of the next one up. Okay. So it says if f prime R is not congruent to 0 modulo p, then R, the solution at the a minus 1 level, can be lifted to a solution S unique modulo p to the a of the congruence at the next level. Okay. So that's the typical behavior, is a solution, one solution at one level lifts uniquely to a solution at the next level. Moreover, the result tells us how to find that. It gives us a formula for S in terms of R, in terms of P, and in terms of T. So T is some new thing that's introduced, and T is the unique solution of this linear congruence. Okay. So this thing here, okay, there's lots of bits to it, but you just recognize it as a linear congruence modulo a prime, okay? Something times t, it's this value, f dash of r, which is non-zero in this case, times t plus this number, f of r divided by p to the a minus 1, congruent to 0 modulo p. And t is the unique solution of that in the range 0 to p. It's a linear congruence modulo a prime, so it will have a solution. Okay, because you just stick this thing over the other side and you multiply both sides by the inverse of f prime of r. And f prime of r does have an inverse because p is a prime and it's non-zero modulo p. So that's the typical behavior. Atypical behavior happens in the case where f prime of r is congruent to 0. And then there's a further test. So within this case, there's 2 possibilities. Either your one solution splits, and you get many solutions at the next level, or your one solution fails to lift. It doesn't correspond to any solution upstairs. So that test is based on the value of f of r modulo p to the a. And here, the typical situation is when f of r is non-zero modulo p to the a. So I've jumped down to the second case. In that case, the r cannot be lifted. Okay. So within this atypical case, within this unusual case where the f prime of r is 0, within that, the usual situation is f of r is non-zero modulo p to the a, and then the solution fails to lift. But sometimes you will find that f of r is congruent to 0 modulo p to the a, and in that case, the r can be lifted to solutions, and it splits into p solutions at the next level. So p different things. Okay. So these are labeled Si from S0 up to SP minus 1. So they depend on this parameter I. Here's the parameter I. And they're just simply gotten by adding on these multiples of p to the a minus 1 to the previously existing solution R. Okay. So that's quite a complex, well, it's a many case algorithm. So there's two top level cases, and then the second of the top level cases itself splits into two cases. Okay. So I think the best thing to do is just to investigate an example of this. And as I say, if we've got time later on, we'll come back to the justification of it. So it's slightly unsatisfactory that we're not doing the justification of it now, but I think it's best to get to grips with it and just to kind of make all these formula and that just a bit more concrete. So the example we're going to use is this one down below. I'll clear the board in case we want to put some stuff on the board. Maybe I'll just leave that there. So the problem we're going to look at is x squared plus 3x minus 16 congruent to 0 congruent to 0 modulo 81. And 81 is, of course, 3 to the power 4. Now, please stop me at any time as we're going through this if you want to ask questions or get clarification. Feel free to do that. So what do we consider first? So first of all, we're looking for solutions modulo 3 to the power 4. So first of all, we consider the bottom case, modulo 3. Yeah. So this is f of x. So f of x will always refer to this top polynomial. So first consider modulo 3. Now f simplifies quite a bit modulo 3. So I'll reserve f. F of x will always refer to x squared plus 3x minus 16. But when you consider it modulo 3, f of x, see, I'm not doing equals there, I'm doing congruent. What does f of x congruent to modulo 3? It simplifies quite a lot. Do I write down x squared plus 3x minus 16? I should simplify things, because if I'm working modulo 3, well, I agree with you on the x squared bit. 0, because it's 3. 3 is 0. Modulo 3, 3 is 0. So there is no x term. Yeah. Sorry? Plus 2? Is there a better way to think of plus 2? Minus 1, maybe. Simpler. Yeah. But plus 2 or minus 1 is the same. So x squared is x squared minus 1 comes 0 modulo 3. So you interpret the problem modulo 3. And this, does that have solutions? What are the solutions to that? Minus 1 and plus 1. Yeah, it's x squared congruent to 1, so it's got solutions -1 and +1. Although to give them their canonical representatives, we'll choose 1 and 2, modulo 3. Okay. So that has two solutions. So you've got two solutions down here at the bottom level. So these are two candidates for R in the theorem that we just looked at. Okay. So we should apply the theorem to each of them in turn. Okay. So we'll take one of them. So we'll let R equals 1. Okay. So now we turn to the theorem. So we have R equals 1. That's a solution to the thing modulo 3. We're now going to look and see if it lifts to a solution modulo 9. Okay, so you look at the top case. The top case asks us to evaluate f prime of x. Now, what is f prime of x? It's 2x plus 3. Nicely. And f prime of r, which is equal to f prime of 1, is what? Is 5. And the point about that, we're just checking that modulo p. And that's non-zero modulo p. Okay, which is the typical behavior for congruence classes, modulo p, to be non-zero. So that means we're into the top bullet point, yeah, because we got a non-zero. So this solution R is going to lift to a unique solution, modulo 9. Okay. So R equals 1 lifts to a unique solution S. And this is given by, so we just follow the formula for S there. S is equal to R, so R is 1 plus T times P to the A minus 1, so plus T times 3. Where T is the solution, T is the solution to this linear congruence modulo 3. So we have 5, we look, it's see the formula, it's f prime r at t, so f prime of r was 5, so it's 5 times t plus f of r. What's f of r? F of r is minus 12. Which we got minus 12 divided by p to the a minus 1, so divided by 3. So we're considering this congruence modulo 3. So what's the solution to that? Well, we just consider it modulo 3. It could be simplified a lot. 5t is the same as 2t. And 12 over 3 is 4, of course, which is the same as 1. So it's 2t minus 1. So it's 2t congruent to 1 modulo 3. And that's true if and only if t is congruent to 2 modulo 3. Yeah? So our t is 2. So the 2 goes into there. And we get our solution S equals 7. So S equals 7 is a solution to f of x congruent to 0 modulo 9. Okay, so we've lifted up from modulo 3 to modulo 9. Okay, and it's still just a single unique solution. So now we'll lift it up to the next level, modulo 27. Okay, so now we're going back into the theorem and applying the theorem again. So just to stick to the notation in the theorem, I'll rename R as 7. Okay, so I've got this solution now. 7 to f of x congruent to 0 modulo 9, modulo 3 squared. So what is A now? A is 3. Okay, so I've got a solution modulo p to the a minus 1. Yeah. Because what is 5 modulo 3? 2. Well, I've divided them first. Yeah, yeah. Is that okay? So it's a minus 1 on the left and becomes a plus 1 on the right. Okay. So now we go into it again and we check f prime of r. So it's f prime of 7. So f prime is still 2x plus 3. So this is 2 times 7 plus 3, which is, what's that? 14 plus 3, 17. So that's still non-zero modulo 3. So again, we're into the first bullet point. So the solution is going to lift uniquely. So r equals 7 will lift uniquely to s, which is given by, it's equal to r, so 7 plus t times 9 this time, where t is solution of the reduced congruence now, which is f prime of r, which is 17 times t, plus, and we have f of r, so we need f of 7. So f, remember, is f of x is x squared plus 3x minus 16. So we need 49 plus 21, which is 70, minus 16 is 54. 4 divided by 9, congruent to 0, modulo 3. And that's true if and only if t is no, still modulo p. You see, so we're looking at equation 7.11 in the notes. It's still this linear congruence is always solved modulo 3. So that's a nice solution, namely. Sorry? No. 0? Yeah, 0. Because 54 divided by 9 is 6, which is 0. 17 is non-zero, so something non-zero times t gives you 0, so t has to be 0. Yeah, so that's the only solution. 0 mod 3. So our t is 0, so actually we've still just got the solution 7. 7 is the still the solution. So s equals 7 is a solution to f of x congruent to 0 modulo, now we're up at 27 now, 3 cubed. Is it? Remember, it's when I said f of 7 was 54, 54 is 2 times 27. Is it? Yeah. Yeah. So we've one more step to go. We've still got, so this original solution, which was r equals 1 down the bottom, it's lifted uniquely both times. So we can finally lift now to 81. So we say for the last lift, we let r equals 7 now, and a now is 4. So we're going to lift to 3 to the power 4, which is 81. f prime of r, which is f prime of 7. Well, we've already done that. We did that in the previous case. Is 17, and that's still non-zero modulo 3. So we go back into the lifting uniquely case. So we go back into the lifting uniquely. Case. So r equals 7 lifts uniquely to s, which is given by s is the r plus 27 times t now. Before it was 9 times t, now it's 27 times t, where t is solution, unique solution, unique smallest positive representative of the solution to, now what are we looking at? F prime r of t, so still looking at 17t plus, and still looking at 54, but this time divided by 27, congruent to 0 modulo 3. So solution to that, well, you've got 54 divided by 27, which is 2. Move it over to the other side, becomes minus 2, which is 1. And 17 is 2. The t is 2. T2. T is 2, yeah. Okay, that's because the intermediate one equates to 2t plus modulo 3. So S is, so finally our solution S is 7 plus 27 times 2, 61. So the claim is x equals 61 is a solution to f of x congruent to 0 modulo 81. Okay. So we should probably check that. So we should put 61 into there to check it. Use Wolfram Alpha or MATLAB or Sage or something. So the polynomial f of x was x squared plus 3x minus 16. Uh, 61. So 38888, and if you do modulo 3888 81, should be 0. 0. That little 0 down there. That's the equal to that. So it's 0. Okay. I think you can do what you do, solve. Yeah, solve mod with the Sage command. You can do solve mod f of x equations modulus. So I think it just assumes that it's doing it equal to 0. Try this. Yeah, 17. They're giving us two solutions, 17 and 61. So we found the 61. That was what the original solution, r equals 1, lifted to. So the other solution, r equals 2, should lift to the 17, as you lift it up through those 4 cases, 4 steps, or 3 steps. 4 steps, 3 steps, 3 steps. Okay. So, do you just want to have a go at doing that? Taking that other solution. So the other solution was so now lift r equals 2 up to a solution modulo 81, and we expect to find the solution, what was it, 17, wasn't it? 17. Is there any questions about that or anything you'd like me to clarify with that? It's fine. It's quite straightforward, I think, to apply it, but it's just there's lots of little legally bits in the algorithm to check, and what I've got it to do there is to give us, I've said, I've done a for loop for n in the range 5, so that means for n in the range 0 to 4. Solve f of x congruent 3 to the n. So solve the 3 to the 0, well, we can ignore that one. Solving it 3 to the 1 is the solution 1 and 2, the first set of solutions we found in that page. So we lifted the 1 that lifted down here, lifted to 7, then to 7, and then to 61. So we should expect the 2 to lift to 8, the 17, and then the 17. So the t, this parameter for that last part should be coming out of 0.
Part of working through these things efficiently is when you're at each stage, always be simplifying. So in this case, times 3, so all these intermediate equations you set up, simplify them through as much as possible.
It's just some other things to notice about this polynomial. So I just tried typing in, just changing the problem slightly. So I changed it to, instead of f of x congruent to 0, f of x congruent to 1, modulo 81. So you try and solve that. Now the thing is, what's this? What are the solutions here? These are empty collections. So there is no solution. So you can see how that arises, because f of x congruent to 1 mod 81, well, the 1 you can bring over the other side becomes a -1, so the minus 16 is minus 17. But when you consider the first of these, modulo 3, it reduces to x squared minus 2 congruent to 0 modulo 3. X squared is congruent to 2 modulo 3, and that has solutions. This is one of the examples where the correct answer is to say nothing, because it doesn't have solutions. Yeah, there are no solutions, because all the congruence classes 0, 1, and 2, which are all of the congruence classes modulo 3, when you square them, you either get 0 or 1. So you never get 2. So no solutions. So there's no solutions right at the bottom. So there's no solutions to lift. There's no solutions at all. But when you consider it to the other possibility congruent to 2, so that would change it to minus 18. So you can see there at the bottom level, modulo 3, there's one unique solution, namely 0, because this thing becomes x squared minus 3, or x squared minus 0. So it just becomes x squared is 0, so that has only one solution, x equals 0. But here you see it, when you lift it at the first stage, it splits into 3 solutions. Then each of those 3 solutions split, oh, well, I don't know, maybe two of them fail to lift and one of them splits again, or maybe they each lift uniquely. I'm not quite sure, I'd have to look at that. But then at the final stage, you can see each of them lifts to 3 different solutions. So you end up with 9 different solutions to that polynomial, modulo 81. You know. So it just shows you different examples. So in the tutorials next, who's got the tutorials next week? John has the tutorials next week. So week after that, we'll return to some of these. But in the meantime, you should practice applying it to a few problems. There's some practice problems there in the notes. But use MATLAB or Sage or whatever to check your solutions and just to guide you through it. So we'll be ready to start the next chapter next week then, quadratic residues, which is a very nice topic.